Today we're going to talk about the moon. The moon, of course, is a pretty close by, so it's actually a system we know more about in many ways than the other planets of our solar system, and certainly much more than we know about extrasolar planets. After all, we've been there, and here's Gene Cernan, one of the last two men to go to the moon on the lunar rover. And Cernan and the other astronauts brought back samples from the moon. So we've learned a lot about the moon's basic properties. I want to talk a bit about the properties of the moon, its formation history. Then we're going to turn talking about cratering on the moon, and then cratering in general, and what we can learn from craters about planetary properties. And then finally we'll talk about tides. First, how the moon raises tides on Earth, and then about tides in general and what they imply when we think about extrasolar planets. So let's begin by talking about the moon. The Earth's moon is fairly large. In fact, it's much larger compared to the Earth's size than basically any of the other moons in our solar system. Mars's moons, Phobos and Deimos, are tiny compared to Mars. Jupiter and Saturn dwarf their moons. Venus and Mercury lack moons. Our moon is pretty large, relatively close, so it actually has a significant impact on the Earth. The distance to the moon is about 400,000 kilometers. That's close enough that some of you will have driven the distance to the moon in your lifetime, and if you were extremely athletic and are good about working out regularly, you can actually run the distance to the moon, though only along the Earth's surface. It's going to be hard to jump that high. The moon's orbit, we can talk about its apogee and its perigee. Apogee is the maximum distance the moon is from the Earth. That's about 405,000 kilometers. And perigee is a bit smaller, 363,000 kilometers. These two are pretty close, so the moon's orbit is close to circular. As I've mentioned already, the moon's fairly large. Its radius is about 1,700 kilometers, or about a quarter of the radius of the Earth, and its mass is about 1% of the Earth's mass. Taking that mass and radius, we can work out its density, and the density of the moon is about 3 grams per cubic centimeter. That compares with the Earth's density of about 5 grams per cubic centimeter. So the composition of the Earth and moon are different, and as we'll discuss soon, that's a bit of a surprise, because we would assume that the Earth and moon were assembled from the same material, and we would expect their composition to be similar. If we look at the structure of the moon is mostly mantle. It's got a thin crust, a core in the very center. The size of the whole core region is less than 500 kilometers, so it's really dominated by the mantle. We've been able to study the properties of the moon by moonquakes. There are meteors that strike the moon. Lots of little micrometeorites are always striking the moon. When they strike the moon reverberates. You hit something, it will vibrate. And because the moon doesn't have an ocean to damp the vibration, moonquakes can last up to well over an hour. We have landed sensors on the lunar surface and are able to use these moonquakes, which propagate through the moon's interior, to probe its general properties. We found that the moon's mostly made of things like silicates. It has relatively little iron and nickel in its core. This contrasts with the Earth. The Earth's composition is quite different. The Earth has a dense core made up of iron. Because of this dense iron-rich core, the Earth's density is much higher than that of the moon. The moon's composition is similar to that of the Earth's mantle. The Earth's mantle, like the moon, is rich in silicates. How do we understand how the Earth and moon formed together? We think they formed out of the same part of the solar nebula. We think they formed out of material that had the same composition, the same ratio of silicon to iron, yet the Earth is much more iron-rich. Where did the iron go when the moon formed? We can think about our current scenario for the formation of the solar system. We think when our solar system formed, the sun was surrounded by a disk of gas and dust. These dust grains coalesced to make bigger grains, and then eventually what we call planetesimals. And this picture here from a simulation from Kakuba and Ida shows what we think the early solar system looked like. And you can see these gaps opened up by more massive planetesimals and planets. And this simulation here shows the evolution of the solar system. So here, early on, we have a thin layer of planetesimals. The planetesimal layer starts to coalesce and form larger objects here. This is called oligarchic formation, as the bigger objects are able to attract more material and grow faster. These planetesimals grow, and eventually we have a situation, and this is measured in astronomical units here, so this is where the Earth's orbit would be, where we have many fairly large planetesimals making up the disk in the early solar system. And what will happen is these planetesimals will start to collide. And this will be complemented by a bombardment of these lighter or smaller rocks that will rain down. And eventually, these planetesimals will merge to form the planets. We think what happened with the moon is a giant Mars-sized planet plowed into the Earth and hit the Earth's mantle, thus stripping off the outer material, having it form a ring, and this ring then condenses to form a planet. And here's a huge Mars-sized planetesimal ramming into an early Earth. We think this collision happened after the Earth cooled. So the Earth had already formed a core, so all the iron in the Earth was in its center, or much of the iron. So when the collision took place, what the new planet was assembled out of, or the moon was assembled out of, was a combination of Mars and some of the rock in the Earth's mantle. There are a number of interesting issues in this, understanding this. One interesting thing about the moon is that the moon's properties are remarkably close to the Earth's mantle. So however we assemble it, we need to assure that the composition of this Mars-like planet, Theia, and the Earth is fairly similar. An interesting idea put forward by my colleagues Rich Gott and Bob Vanderby is that Theia itself was assembled quite close to the Earth and was made up of very similar material to the Earth, because it was assembled at the Earth Lagrange point. If you'd like to watch an interesting simulation of this, there'll be a link that will take you to this YouTube link, and you can watch a video showing the collision between Theia and Earth, and the simulation showing how, in a very short time, the disk around it cools, condenses, and forms the moon. Now, this process of collision between planetesimals and the eventual bombardment by the other rocks that make up the remnants of the early solar system plays an important part in solar system formation. In fact, these rocks continue to rain down upon us. And as we'll talk about later in the course, we talk about evolution on life on Earth, we think that it was collisions, not this big, a smaller one, but collisions like this that probably wiped out the dinosaurs. One of the exercises I'd like you to do is to work out the energetics of an impact. And as you'll see, when a collision takes place, an enormous amount of energy is released. The way we can estimate the energy released is to compute the kinetic energy that the incoming planet or planetesimal brings to the Earth. The kinetic energy in a collision is going to equal 1/2 the mass of the incoming material times its velocity squared. Now, the Earth is moving around the Sun at about 30 kilometers a second. So a typical velocity here is going to be about 30 kilometers a second. So we want to plug that in. If we want to keep our units the same, so we're working in units of joules, we want to measure mass in kilograms and velocity in meters a second. So we want to write this as 3 times 10 to the 4 meters per second. And what you'll do in a moment is take these numbers, plug them in, and work out the enormous energy that's released when a Mars-sized rock strikes the Earth, and work out even when a relatively small incoming meteor, something weighing, say, 1,000 kilograms, strikes the Earth, even that kind of collision, which happens fairly frequently, even today, releases an enormous amount of energy. So that's the next problem you'll do. I want you to work through those numbers, then we'll come back and we'll talk some more about the effect of these meteors forming craters.